Hi everyone, hope you liked the previous video. So in previous video we started with this basic assumption that time passes faster when you are away from the gravitational pull of a massive object and slower when you are close to the surface of it. Okay. But why is it happening? And even a more good question is basically how is it happening? What's the math behind it? So to explain this, I have to call my friend Tom Cruise. He's an astronaut by the way in my video. Okay. So if you have watched the previous video, you know that I'll tell you story from both perspective, from my perspective and from Tom's perspective, and not only tell you the story, but I'll also mathematically explain you how is it happening and what's the science behind it. And let's go to the mathematical part directly. Okay. To explain this, I'll need a device called photon clock here. Photon clock. And you can ask a simple question, why photon clock and not a normal clock? Well, my friends, you can take a normal clock too, and it will behave the same way. I promise it will be clear to you by the end of the video. But photon clock is just simpler to explain the time dilation. Okay, so photon clock is a clock basically with mirror at both the ends, and these mirror will reflect the photon. Okay, so there is a photon in between, and to measure time in this clock, it's basically photon has to go up here and come back, and this would be one tick in this clock. Okay, so what's happening in Tom's photon clock? So as you know, the speed of the photon is same as the speed of light. So here the speed of photon will be c, and let's say the time that it took from going here to up to this point. Let's say this is the actual time that Tom is seeing. So now the distance would be speed into time, that is c into t. Okay, from my perspective, what's happening, this same photon will take time t dash from going here to here, and since its speed is c, so the distance would be c into t dash, and here this t dash is basically the dilated time that we are feeling. Okay, so let's combine this, let's add these two scenarios here, so we will get a very good looking right angle triangle, my friends. Okay, so the distance for this length is c into t, and the distance of this diagonal length is c into t dash. If we know somehow this distance, we would be able to figure out what would be the dilated time. Okay, now as we know, the ship is moving in the direction forward and its speed is v here, and it's going from this point a to this point b in the dilated time t dash. So this length would be v into t dash. Now we just have to call Pythagoras uncle to solve our problem. So as you know, Pythagoras theorem is basically for any right angle triangle, a square plus b square equals to c square. So if this side is a, this side is b, this side is c, it's simply the length would be a square plus b square plus equals to c square. Okay, when we reshuffle this formula, we will get this value and ultimately this value. So just to clarify, this is the time that astronaut is feeling, that is Tom is feeling, and this is the time, the dilated time that I am feeling on Earth. Okay, so we can rearrange this formula as t dash equals to t divided by 1 upon under root 1 minus v square divided by c square, and this 1 upon 1 minus blah blah blah, it's called as Lorentz factor gamma here. So you can also write this as t equals to gamma into t. So this t dash is our dilated time. Okay, so suppose if in Tom Cruise's spaceship he has been there for 100 seconds, and if he's going by the speed approximately 0.87 of speed of light, then it would be around, if you calculate by this formula, our t dash would be something around 200 seconds. So even if you travel around 87% of the speed of light, it's like only the time dilation is only double. So to feel the time dilation, you have to actually move very fast, very you have to move close to the speed of light actually. And to actually feel the time dilation, you have to sometimes move around the speed 95% to 99% of speed of light. Okay. And even if you travel, suppose at the speed of 50% to the speed of light, the time dilation that you feel would be just 1.2 times. But is time dilation really happening, or it's just some kind of mathematical illusion that is presented to us? Let me tell you, my friends, it's actually happening. So one of the example for this, and it's really a famous example. So there is this particle muon. This muon particle, its half time at the surface of Earth is kind of 1.56 microseconds. What is half life? So half life is basically, suppose if we have 100 muons here, due to the electromagnetic decay after half life, that is 1.56 microseconds, this 100 muons particle will be 50. Again, after 1.56 microseconds, it would become 25, so on and so forth. So when these muon particles put above to the surface of Earth, so suppose this is the surface of Earth and there is this muon particle. When we move this muon particle very far above to the surface of Earth, the half lifetime of this muon particle increased by almost 10x. So this is the clear example of how time dilation works in real life. Even our scientists who are there in International Space Station, so it was directly checked when two perfectly synced clocks, one at the surface of Earth and one at the International Space Station, they were checked. Kind of there was some difference between the time in two actual physical clocks. So this is another example for the time dilation. Spoiler alert for the interstellar movie lovers. When Matthew lands on the Miller planet, I think it was close to neutron star, something was that. Anyway, if we don't go to the physics that how Matthew landed in such a strong gravitational force, if Matthew would have been actually landed, he would have been fatke flower ho gaya hota, if I'll tell you in Hindi. So let's not go to the nitty gritties. But if you see from the time dilation perspective, what's happening, 1 year on that Miller's planet, or no, sorry, not 1 year, 1 hour in that Miller's planet was actually 7 years on Earth. So 1 hour there is around 7 years on Earth. That is because the gravitational force on that Miller's planet was so strong. Because I think it's close to it was close to neutron star, or it was a neutron star itself. I was not sure. It has been a long time since I watched that movie. But the point is that the gravitational force has to be really strong, even to feel time dilation at the surface of suppose on sun, and you are watching it from the surface of Earth, it would be not that strong. It has to be something like black hole or neutron star, where the space time is very curved. There is one more aspect to this story, and that is even more interesting. That, my friend, is length contraction. So it's not just about the time, it's about space and time both. So why should time have all the fun? So in next video we will discuss about maybe length contraction. So that's the end of this video. If you liked it, do share it, subscribe to my channel, and leave comments with your thoughts. Thank you everyone.